Over to you, Dan.
Kelly, thank you very much, and thank all of you for joining us today. Before we get started, I first of all want to thank you for a number of you who've joined us throughout the year. We appreciate your interest and obviously committed time value for joining us in these webinar sessions. And personally, for me, as this is the last one for 2023, I wish all of you a very happy holidays and a happy, prosperous, healthy new year. Before we begin today, I want to thank the manufacturer we represent, Air Fixture, for most of the material presented today. They are a terrific resource and on the cutting edge of the development of underfloor air technology. So I had to acknowledge their expertise in providing a lot of the good material that we're going to be giving you today. Today's agenda is somewhat diverse. Well, it really is just focused on UFED technology. We've covered a lot of other topics that apply to underfloor air distribution and thermally stratified environments. So at the risk of just being a little bit redundant, to reacquaint ourselves with some of the technologies, we're going to cover them again. But before we do that, we're going to explore context. Why UFAD? Why is UFAD getting more and more attention nationally as a solution for better indoor air quality and reducing the risk of infection? If I'm not mistaken, the Clean Air in Buildings symposium held at the White House last October actually acknowledged the room they were in had an underfloor air system, and there was a reason why they did that. Hopefully we'll demonstrate why today. Then we're going to look at underfloor air systems. We're going to look at UFAD design considerations and strategies. We're going to look at UFAD air handlers and how they are currently being designed and laid out to reduce the mechanical footprint in buildings. And then we're going to look at the biggest nemesis of UFAD applications, plenum leakage, what to look for in plenums, and how a manufacturer's rep should be able to support a project to minimize leakage to create successful UFAD installations. So before we do that, let's begin this session with air patterns and pathogen migration. My gosh, this goes right back to pandemic days. Don't hold it against me for going back a couple of years now to a topic that was really ever present before us. But that event, the pandemic, is influencing how we look at HVAC today. ASHRAE has actually launched their 241 standard, which is advocating for buildings to be designed with infection risk management modes that will increase the equivalent clean air value, or CFM, at the breathing zone when buildings are assigned to go into IRRM mode. So be aware of that. That standard 241 per the forward other standard says that it will be adopted, incorporated into 62.1. And of course, we know that that is the standard municipalities use for their building design evaluation. So be aware the industry is changing. So anyway, let's look at what influences the risk of infection. And one could argue, you could argue perhaps maybe even contaminants within a space, as indoor air quality is getting more and more attention today. Anybody who is sick, who coughs and sneezes, or even breathes in a room expresses virally laden droplets. And if these droplets are ejected into a room that is not properly humidified, those droplets desiccate very quickly. The water in the droplets evaporate within a couple of seconds, and releasing any pathogens that might be in that droplet into the air. And those desiccated viruses are lighter, they are buoyant, and they will stay in the air for a prolonged period of time, 24, 48 hours, possibly even more. So low humidity environments increase desiccation rates of virally laden droplets, allowing for aerosolized pathogens to be released into a space. Higher humidity environments equals lower desiccation rates, which is what you want, so the droplets maintain their mass and allows gravity to draw them from the space. ASHRAE recommends a relative humidity environment of about 40 to 60% RH. And of course, we know that when we're in flu and cold season here in Arizona, it is our driest time of year, as it is in any other part of the nation. So what does ASHRAE's position document on infectious aerosols had to say to us? Some of the wisdom they provided was the majority of larger emitted droplets are drawn by gravity to land on surfaces within 3 to 7 feet. From the surfaces, they can be transmitted fulmitically, hand to mouth, surface to surface. General dilution ventilation and pressure differentials do not significantly influence short-range transmission because the droplets are too large to be impacted by local air velocity rates in and around the sick person. Conversely, dissemination of smaller infectious aerosols, including droplet nuclei resulting from desiccation, can be affected by airflow patterns in a space in general and airflow patterns surrounding the source in particular. The following HVAC strategies have the potential to reduce the risk of infectious aerosol dissemination: air distribution patterns, differential room pressurization, personal ventilation. And I want you to take note of air distribution patterns and personalized ventilation because they are applicable to underfloor air systems. Also, the opportunity of looking at increased outdoor ventilation, which I've been speaking to throughout the year. The Epidemic Task Force addresses ways for reducing the risk of infection. And one of those solutions, of course, is air distribution patterns in a space. It goes on to say that regarding air distribution, that when directional airflow is not specifically required or not recommended as the result of a risk management, promote mixing of space air without causing strong air currents. So ASHRAE recognizes the importance of creating a mixed air environment. So let's quickly review a conventional HVAC design to promote and create a mixed air environment. From previous sessions, maybe you'll recall that supply air is injected at high velocity at 55 degrees. And you should see a terminal velocity out of the diffuser of 150 feet per minute, so air can achieve Coanda along the surface to which it's supplied across, inducing room air into the jet that allows for proper mixing of the air in the room. So room air is induced into the jet, and by this application, or through this general mixed air, or this supply air strategy, a mixed air environment is created where you have a uniformity of temperature throughout the cubic volume of space of plus or minus 2 degrees to meet ASHRAE standard 55. However, what about when we are at part load conditions and you have a building that either cycles on and off with packaged rooftop units when room temperatures are met? Or what about variable air volume systems? VAV boxes go from 100% open, which we see during our peak load design conditions, which are in summer, and throttle back down to 50%, if not low, of the airflow. Consequently, the discharge velocity at diffusers is minimized. You are not getting proper mixing in the space, dumping results, and consequently, any contaminants or pathogens within the room will become more localized in concentrations build in those areas not exposed to higher air velocities. There was a study done, a CFD model done by Holt Architects, that demonstrated what happens with virally laden droplets as they're expressed by an infected individual. Large, heavy, virally laden droplets hang lower in the room after they've been ejected because of their mass and weight. Gravity does its work, and it draws those droplets to the ground out of the air where they cease to be less of a hazard. Small droplets and aerosolized virus, however, are more buoyant, and they travel long distances in the space. In fact, if somebody sneezes and ejects virally laden droplets into the space, those droplets leave at a rate of 44 miles per hour, and they project easily up to 26 to 28 feet across a room if the room is large enough. So Anyways, you can see a conventional mixed air system is conducive for spreading viruses. And I'll bet you anything this CFD model was based on a thoroughly mixed air environment at high velocity. Well, are we at peak load during our flu and cold season, the season that we're at right now in buildings? And the answer is no, we don't even have a mixed air environment. So consequently, it does beg the question whether or not the spread and the risk of infection is greater now when we're at part load conditions. But what if air, instead of being injected into the space at high velocity from ceiling diffusers, were supplied from the floor to create a vertical airflow pattern? What if a thermally stratified environment is created in a space and convective thermal plumes or heat plumes within the space actually move the air in the room and not fan energy? What would happen to contaminants and the risk of infection if a vertical airflow pattern was adopted, whereby a piston of conditioned clean air rises from the floor across the breathing zone and is evacuated from the space through return and exhaust grills mounted in the upper levels of a room? To give you a visual of what this could mean, Airfixture provided us with this rather compelling graphic. I think it's excellent to show you the overall conceptual differential. Well, this looks wonderful conceptually, but is it actually effective? A study was done by 3 Japanese engineers or scientists, I really don't know their professions, quite frankly, where they looked at a building that was 66,000 square feet, 1,194,000 square feet, structural steel building. And it was a mixed-use building of offices, retail, and exhibition spaces. And they used this to evaluate the difference between an overhead mixed air system and a stratified air environment. What they found using laser scanners is that particle counters was that in the underfloor air system, the contaminant density of 1 million particles per cubic foot was read in an underfloor air system, a building conditioned by underfloor air. However, in the overhead system, they registered a particle count of 3.5 to 4.5 million particles per cubic foot. Consequently, they came to the final conclusion that levels of airborne particles on floors with underfloor air distribution were 71% to 77% lower than floors with overhead air distribution. Well, that's pretty interesting, and it certainly does draw one's attention. Nature magazine also published a report in 2022 in their scientific reports where a CFD model was generated, and the article was written. The article's name is Quantitative Evaluation of Precautions Against the COVID-19 Indoor Transmission Through Human Coughing. Specifically, it's very specific, but regardless, it certainly does apply with aerosolized pathogens in a space and how they behave. So the study synopsis consisted of this. It was to focus on the dispersion of COVID-19 laden droplets using CFD modeling and simulation of the coughing process of virus carriers in an enclosed closure room, and to set up a basic prototype of popular precautionary strategies, that is to say face mask, upward ventilation, protective screen, or any combination thereof. And what were their findings that was published in Nature? The result shows that implementing upward ventilation is the most effective measure, followed by wearing masks in a space. The soundest solution is to reduce the risk of infection in a space, the article proposes, is the combination of the face mask and upward ventilation, which can reduce the indoor infectious concentration by nearly 99.95%. It goes on to say that upward ventilation forces the droplet cloud to follow the venting air, which is from the occupied zone to the upper levels of the room, thereby reducing the risk of infection. So that's pretty compelling. So what type of system will provide for an upward airflow or vertical airflow solution to a building? Well, underfloor air systems, they are that system to be considered. So what is UFAD? What is an underfloor air system? It is a system whereby building supply air is delivered through diffusers mounted in the floor. The conditioned room becomes a partially or fully thermally stratified environment. If you recall from previous sessions on thermally stratified environments, the actual airflow mechanics involved in these systems and how they differ from a mixed air system. Conditioned clean air supplied to the occupied zone for a single pass of clean air across the occupant breathing zone occurs. And consequently, warm contaminated air is exhausted from return or exhaust grills mounted in upper levels of a room. How is this done? A UFAD system uses a raised access floor approach, whereby 2x2 floor panels are mounted on pedestals within a space. All mechanical, duct, and IT cabling and electrical are under the floor. There's no reason for maintenance crews to get up on ladders to service any part of an HVAC system or any other serviceable item within that space or within the building. The plenum then is pressurized with air in order to cause air to flow through underfloor air diffusers that are located in the floor panels throughout the building. So what are the occupant and owner advantages? The advantages: improved thermal comfort, no drafts. They are conducive to lead serviceable points because each individual has the opportunity to have personal airflow control at their personal diffuser. And if you recall from ASHRAE's guidelines, personalized ventilation is one of the solutions for reducing the risk of infection. That is an inherent quality of an underfloor air system. Vertical airflow for improved occupant air quality, a single pass of clean air across the breathing zone. Flexible response to zone load changes. You don't have to worry about being in the airstream provided by an overhead system at high velocity. Wherever there's a heat source, the cool air is going to go to, because convective plumes will be drawing the cool conditioned air to them due to the upward flow air movement of a convective plume. Consequently, space heat generating sources automatically draw air to them via convective plumes. There is no rebalancing of a system to track transient loads within a zone. These systems are more energy efficient than conventional systems because they are low pressure. Systems are not designed like in a VAV box to provide a minimum ½ inch at a VAV diffuser. Plenum pressures are designed at 0.05 to 0.08 inches, possibly 0.1 inches of pressure, a significant reduction in fan energy. And also in Arizona, where we are dry in our shoulder seasons, fall and spring, we can actually double economizer hours because air supplied by underfloor air systems is not at 55 degrees, it's at 65 degrees to prevent thermal comfort issues of overcooling feet and ankles. So that results in about a doubling of economizer hours in Phoenix, Arizona, to roughly about 34 to 35% of our annualized hours. Owner advantages: less overhead ductwork, reduces floor-to-floor ceiling heights, open ceilings to showcase architectural features. These systems are ideal for a growing demand in our market for mass timber construction or mass timber buildings. There's an opportunity for increased window sizes to improve daylighting, better indoor air quality as recognized by ASHRAE 62.1, and we'll address that shortly, and reduce churn costs. If an owner wants to remodel an open floor area, changing ductwork locations is not required. Moving 2x2 panels may be desired. It's a lot easier than changing out ductwork. You don't even have to readjust the diffuser sizes necessarily for those applications. So there's an attractive life cycle cost advantage for owners who adopt underfloor air systems. So what do these systems look like? Well, you start with a bare floor And please be aware, these floors do not need to be polished, which is a construction savings to them. Because of the pedestal application, they can be easily mounted on coarse concrete floors while maintaining a level plane of floor above them. So the pedestals are mounted first, and any cabling that are associated with them would be installed. The floor is then installed. Each of the tiles are pre-cut by the floor manufacturer, and consequently, when it comes for the mechanical contractor to install the diffusers, they just bring the diffusers to the hole, pop them in, and secure them firmly to the panel. Be aware, you want to make sure you have a manufacturer that has a securing capability of the devices to the floor panels. Not all of them do, and it would need to be addressed if you're considering looking at and designing to an underfloor air system. Carpeting is then laid over the top of the floor panels, and the carpeting is essential to help the plenum maintain pressurization. Now, it's not required, providing the floor manufacturer such as Tate is aware that carpeting will not be used. There are strategies to seal the panels more effectively for an exposed floor. Also, where the carpet tile is located is critical. This slide is actually incorrect. You want the tiles to overlap the seams of the panels to add just a little bit more security of securing the plenum from air leakage through the floor itself. Then furniture goes into place, and then the devices, the building is commissioned, and you have occupants, and this is how the floor actually looks upon completion. As you can see, the diffusers are located at each occupant in their cubicles, and this again conforms to ASHRAE's Epidemic Task Force guidelines for personalized ventilation at each occupant. So you have that advantage with the UFAD system. Underfloor air designs, however, had a rough road in the early days. There was a bit of a learning curve at first, and the ASHRAE UFAD design document that was generated in the early 2000s was actually pulled from the shelf, I think, in 2010. Mike McQueenie, who is president of Airfixture, the manufacturer we work with, actually sat on the ASHRAE committee that rewrote the UFAD guide, which was completed in 2013. A lot of lessons learned, and UFAD today really does bring a very compelling HVAC solution to our market today to address our issues of energy efficiency and better indoor air quality. So the air side component, how is air delivered to a space to create a semi or fully thermally stratified environment? Air is supplied through each diffuser in the floor or in perimeter zones that would provide cooling and heating linear troughs. And air is supplied at 63 to 68 degrees to prevent overcooling of ankles and feet. I remember my mentor in the industry, Jerry Sipes, who was VP of Price Industries at the time, told me that he actually achieved his PhD in mechanical engineering studying thermal comfort at Kansas State University. And they actually determined that providing the temperature differential from the foot to the head remains within 5 degrees, an occupant cannot discern the temperature differential. And that's what UFAD systems are designed to in the occupied zone, which is defined as 6 feet off the floor and 1 foot off the wall, a temperature differential of no more of 0 to 5 degrees for a standing occupant. Air needs to be properly dehumidified, which means the air handlers have to be properly designed so that the air is humidified before it's supplied at 63 degrees, which means air has to be brought to dew point at the cooling coil. Conventional designs are 55 degrees. I think we need to go beyond that to more like 52, and then warmed up again to a 63-degree temperature to supply these systems. There are technologies we'll cover at the end of the presentation and air handler layouts that are conducive to do this. So, sustainability benefits for UFAD systems. Reduced run lengths of ductwork. Consequently, you don't have a lot of galvanized sheet metal to be addressed at some time down the road from the building, certainly if it's to be remodeled. Promotes the reuse of materials. Wire and cable is minimal. In fact, wireless systems are available today. You don't even need to run cable underfloor to service variable air volume floor diffusers or linear or perimeter linear troughs. Reduced ductwork, drop ceilings can be eliminated, reduce slab to slab floor heights in a building. A lot of material savings need to be addressed before UFAD is assessed as a mechanical comparison to conventional HVAC. There are a lot of architectural features that are architectural aspects that benefit from UFAD that should be included in any building owner's evaluation of which system to apply. ASHRAE recognizes the effectiveness of UFAD systems, and it has assigned it a ventilation effectiveness rating of 1.2, which means if applied, 20% less outside air is required to meet code. And 20% less outside air does offer a lot of energy efficiency. Well, why is that? Why is air quality better at the breathing zone? If you look at the graphic to the upper right, it demonstrates how a mixed air system is doing its job if it uniformly dissipates contaminants and pathogens throughout the cubic volume of space. However, in a displacement ventilation system or a UFAD system, because of the convective plumes, contaminants and viruses tend to drift upward into the upper levels of the room where the exhaust grills are, so you have a higher concentration of contaminants in the upper level of the room where they're evacuated, exhausted from the space. Sensible load calculations need to be considered. In a UFAD system, in a thermally stratified environment, and I've covered this before, you only design to the occupied zone, which is defined, as I mentioned earlier, at 6 feet high off the floor and 1 foot off the walls. The upper 1/3 level of the room, or higher if you have 14-foot ceilings, that sensible load would not be included in the BTU sensible calculation of the occupied zone. Now that load would have to be considered at the cooling coil of the air handler, but for calculating your air volume rates to the occupant zone, they would not necessarily be included. One thing you do have to be aware of is that what is the orientation of the building and where is the rising and setting sun in relation to the floor panel and the consequent radiant effect of a sun showing on a floor. That would have to be taken into an engineer's evaluation of load calc, but it's something that should be addressed, and it shouldn't present a problem if it's considered during design phase. There are two approaches to air delivery solutions using UFAD. The traditional early design was semi-turbulent, that is to say, high velocity discharge air emitted from the diffuser creates a mixed air condition in the occupied zone. Look at it as a micro mix zone. Thermal stratification occurs above the occupied zone. However, because the occupied zone is at space set point, which we anticipate to be 73 to 75 degrees, the thermal plume from a 98-degree occupant, hopefully 98 degrees, will still cause that air from the occupied zone to rise up with the plume into the upper levels of the room, carrying contaminants and pathogens with it. The other solution is displacement ventilation. It's another UFAD strategy. Air is ejected into the space at low velocity and horizontally across the floor to create a fully thermally stratified environment from the floor up through to the ceiling or to the deck. These are two strategies. The displacement ventilation strategy offers perhaps better thermal comfort because you have low velocity discharge and reduced risk of cooling ankles, if at all possible. However, because the airflow through them, as I'll demonstrate shortly, is less, you need more of those diffusers. So the first cost is marginally more. The semi-turbulent design injects air at a higher velocity, so you get more airflow, you need less diffusers, and it offers a less expensive first cost solution. Both applications today meet ASHRAE 62.1, 1.2 ventilation effectiveness in the design. So take advantage of that. This is the direction you're going to go in a future design. So let's look at a high velocity discharge air or semi-turbulent air underfloor air solutions. Supply air is injected into the underfloor plenum. Plenum depths are about 8 inches to 20 inches. In the past, when I was promoting underfloor back in 2010, 2012, we would have to design to 16-inch plenum heights because we had fan terminal units under the floor that I'll illustrate shortly. That is no longer necessary with the newer technologies that are available, and again, we'll demonstrate why here shortly. The plenum pressure needs to be uniformly pressurized. That's another aspect to underfloor air systems. And I know our manufacturer, and I'm confident there might be others, our manufacturer will help lay out the duct injection points to effectively distribute the air to maintain a uniformity of plenum pressure throughout the plenum. And that is critical. When you're pressurizing a plenum to 0.05 to 0.08 inches, the airflow through the diffusers is pressure dependent. The amount of air out of a diffuser is dependent upon the pressure local to that diffuser. So if you have pressurization swings throughout the plenum, you're going to have swings in airflow out of the diffusers. But again, a properly designed system eliminates that concern about an unevenly pressurized plenum. Air in these semi-turbulent designs terminates at about 4 to 5 feet above the floor, thereby creating an occupied zone of mixed air and a uniform temperature throughout the occupied zone. So plenum pressure equals airflow, change of pressure equals change in airflow. Plenum pressure uniformity is required. A semi-turbulent diffuser designed at 0.05 to 0.08 inches supplies air at a volume of 80 to 100 CFM per 8-inch diffuser. Now be aware, manufacturers make 10-inch diffusers, and there are even some rectangular or square diffusers that provide even more airflow in areas where you don't need to have that dedicated diffuser for occupants to improve the indoor air quality at that occupant's breathing zone. These diffusers can come in either a constant volume or a variable volume airflow solution that the variable air volume diffusers actually adjust the flow rate at the given plenum pressure to meet space temperature set point at the thermostat. Mixed air or semi-turbulent designs also result in thermal stratification, but above the occupant zone. We would anticipate 80 to 85 degrees above the occupied zone. It could be tending more towards 85, the taller the ceiling. So if you have 12, 14 foot, 15 foot ceilings, that upper room air temperature, of course, could be greater depending on the sensible loads in the space. Higher level of contaminants occur at the exhaust, consequently for better indoor air quality. A semi-turbulent design does conform to the principles of a thermally stratified environment. So what about a displacement ventilation solution? Supply air is injected into the underfloor plenum. Plenum depths can be designed at 8 inches to 20 inches. Again, all the properties of the semi-turbulent underfloor plenum apply, uniformity of pressure. And however, the air is discharged through a different type of diffuser face, low to the ground at lower velocity to allow for full thermal stratification throughout the cubic volume of space. These diffusers at 0.05 to 0.08 inches can supply 52 to 70 CFM through an 8-inch round device. These devices too can come in 10-inch, a 10-inch size. And by the way, the semi-turbulent and the displacement diffuser, I see I have that not properly titled. It says semi-turbulent diffuser. It should say displacement. I apologize for that. Anyway, these diffusers, you'll need more of the diffusers at the lower airflow provided because they're unable to discharge the same volume of air. So there's a cost impact to that. Again, thermal plumes occur with a displacement ventilation UFAD solution, thermally stratified environment. All the other properties as the semi-turbulent take place. I don't know, I'm not aware of any studies that say displacement offers better IAQ than a semi-turbulent design. I have certainly not read that and have not uncovered that, but who knows what further future studies might come up with. So be aware of that. UFAD systems are inherently quiet. Very little noise in the space, if any at all. If you have an improperly pressurized plenum in some regions that result in higher discharge air than designed, you might hear some rushing sound of air through the device, but that would be due to an imbalance in plenum pressure under the floor. So what are the UFAD design considerations to keep in mind when you're laying these systems out? Well, first of all, again, to review, the advantage of UFAD is that there is a low investment cost. No duct work under the floor is required. You don't have a lot of galvanized sheet metal hanging around in your system to be dealing with. No balancing dampers to adjust to make sure air is at the appropriate flow rate at each register and diffuser in order to create the proper flow rates in an environment. Diffuser placement is very flexible, and UFAD plenum heights can now be supplied at 8 inches deep. And I keep mentioning that over and over again because that could mean a lot in a multi-story building in the ability for an architectural design to reduce the floor-to-floor heights in a building. Supply air in these designs traditionally and in the early days were injected on the interior zones of the UFAD plenum. They were injected at a high enough of a velocity to project the air across the plenum space. However, in these designs, one has to be very careful that such an injection point is not along a wall where the air will achieve coanda along that wall and create an imbalance in plenum pressure within the space. You have to be very careful of how you adopt this injection strategy. The old days, you used turning vanes at the injection point to allow for a wider distribution of supply air out of the register to promote uniformity of pressure under the floor. That's how it was done in the older days. Another solution in the old days was to have ducted floor diffusers. I remember this is what the University of Arizona required or asked for when GLHN laid out their Environmental Natural Resource Lab. All the interior spaces had UFAD, and the owner wanted all those diffusers to be ducted. They were concerned that students might be tempted to pour their big gulps down the diffuser floor as a joke. Mind you, if that got into the ductwork, that could provide a bigger pain in the neck than trying to clean up a floor plenum. Anyway, it certainly was out there in the old days, this solution. It is certainly not necessary, and I can't see any reason why it might be considered. How do we condition the perimeter zone of a UFAD system? The traditional way of doing it is line the perimeter floor with a linear diffuser and supply air from a fan-powered terminal unit. The problem is those fan-powered terminal units are deep. They have a fan in them, as well as they come initially with filters as well. And those fan assemblies require plenum heights of 16 inches, 14 to 16 inches, so they'll fit under the floor. And that's why plenums were designed to that point. Now, there could be an application in an office building or in a building with conference rooms that might suffer large load swings, go from 0 occupancy to 20 occupants very, very quickly for a meeting, where there could be a fan-powered strategy considered, but we would certainly want to work with the design team in doing that. But anyway, this is very much an older strategy today compared to the newer technology that I'm about to demonstrate. For perimeter zones, we now use plenum trough diffusers that have a damper at the inlet that will adjust from a two-position damper that goes open or closed, or it can actually vary in a VAV system in cooling mode. And this diffuser comes with a heating element inside. You can either use an electric coil or a hydronic coil to provide perimeter heating during our colder winter months. But in the summer, it will have a VAV characteristic where the damper that allows air from the plenum into the trough itself to modulate, thereby regulating airflow to maintain thermal comfort at the perimeters. With this technology, it does, and certainly in our desert environment where we don't have a high heating load, this is your heating solution. And consequently, you don't need a fan terminal under the floor, which means you don't need as deep a plenum height in order to provide the adequate air necessary for these perimeter linears. Consequently, plenum heights can be designed at 8 to 12 inches. We would certainly want to look at that. And it certainly reduces the mechanical maintenance of systems underneath the floor. No more fan motors that need to be looked at. No more no longer would tiles have to be raised to evaluate and service fan-powered terminal units. Everything is serviced through the face of the linear trough register. So this is how they look in design. And as you can see, that air is injected through a vertical air column, an air handling solution that I'll address later in this presentation, that projects air to the perimeter, whereby plenum pressure drives the cool air to the perimeter troughs, or in heating mode, the dampers to the plenum go to a closed position. The heating element is enabled, and warm air services the perimeter wall via convection. One of the things that one has to keep in mind in designing underfloor air, and again, this is an aspect that we would evaluate with any design engineer and how to overcome this, is thermal decay. Thermal decay did present challenges to UFAD systems in the early days. And let's think about why, and this especially occurred in multi-story environments. If air is injected at the interior zones of a UFAD plenum, that air has to migrate across the surface of the concrete slab. If the air under the slab is at 80 to 85 degrees, the conductive heat effect through the slab will heat the supply air in the plenum. And the longer the air has to travel under the plenum, the more heat is absorbed into that supply air. So consequently, the air supplied at diffusers at the perimeter zone will be warmer than the air coming from diffusers mounted on the interior zone. And this resulted in some troubled UFAD projects in the early days, because thermostats would regulate diffusers to meet the perimeter load, causing overcooling to occur in the perimeters, in the interior zones of a space. So that conductive heat effect has to be addressed. Studies have found that for every 5-degree increase in the floor slab above supply air temperature, the supply air temp will rise 2 degrees for every 33 feet of plenum distance traveled. So the current practice in laying out underfloor air systems and the injection point of supply air into the plenum is to be at a maximum distance of 50 to 60 feet between the floor grill and the UFAD supply duct. New technologies, however, are now applied that allow for an even more effective dispersion of properly tempered air through diffusers, especially at the perimeter. It was UC Berkeley's Center for the Built Environment, to my understanding, that came up with this understanding called reverse flow, and is adopted by DuckSox in their UFAD SOX design, 10, 13 years ago. Using fabric duct in those days, you could actually bring the supply air to the perimeter, where the coolest air is available to the area which has the greatest load. And then you allow that warmer air gained through thermal decay to backfill into the interior zones, which is more than adequate, because in this way you overcome the overcooling on the interior zones. And this design is more conducive to a successful UFAD layout. And Air Fixture themselves have actually taken this even further and have demonstrated, and you can use sheet metal ducts as well, that you can do higher velocity discharge air. And I don't remember if it was 2,000 feet per minute or 3,000 feet per minute. Doesn't necessarily provide the sound challenge that you might consider. And if you inject that air at high velocity to the perimeter, you can overcome the overcooling of interior zones by providing an adequate amount of properly conditioned supply air to the perimeter when you're in peak summer cooling condition. So what are the air handlers that service underfloor air systems? Well, I can assure you they're not your conventional medium pressure VAV air handlers. It would adopt the same type of air handler layout possibly as we found in displacement ventilation. Side stream bypass is an effective solution whereby a plenum with a modulating damper located before the cooling coil is provided, and that plenum discharges after the coil. A discharge air temperature sensor is mounted at the discharge of the air handler, and to maintain at the supply air discharge temperature, the mixed air damper modulates open and close to allow mixed air at a higher temperature, possibly 80 to 82 degrees, into the airstream of the cooling coil downstream to provide free reheat. You want to avoid reheat at all costs because it's very expensive. This solution, however, does demand, as I covered in Psychrometrics Deconstructed Part 2, that the dehumidification of the supply air off the coil is adequate to absorb that latent gain in the mixed air, certainly in Arizona during our monsoon months. There's another solution that uses a dual tunnel design where you have an enthalpy wheel and a sensible heat transfer wheel. The enthalpy wheel preconditions the outside air, so you have for enhanced energy efficiency. And the sensible unit actually uses the thermal energy off the return air to post-heat the supply air off the coil. This solution does offer better control, better temperature control to maintain a properly dehumidified 63-degree supply air solution. However, you do have a static pressure gain through the secondary wheel, the sensible heat recovery wheel. That would have to be taken into account regarding energy performance or energy modeling of a system of this kind. There are also custom and semi-custom DX solutions. We have Daikin, we have Annex-Air for fully customized DX solutions that can use hot gas reheat off the cooling coil to provide the appropriate discharge air temperature out of the unit to service a UFAD system. However, there's a newer technology today, and Airfixture has certainly advocated for it and actually manufactures this device. It's called an air column. Air columns are mounted in the building itself in mechanical closets. These mechanical closets are potentially 50% smaller than you might see in a medium pressure VAV indoor air handler application. They're very quiet. They allow for lower building heights. You don't have a lot of mechanical equipment on the roof of a building. They provide tighter control for more energy costs, certainly low static pressure requirements for the discharge of air into the underfloor plenums, create greater flexibility of building design, and they are also conducive to 8-inch floor plenum heights. We can also do these units with variable refrigerant coil technologies, which adds a very attractive option to the space, and that's its own topic in itself. This is a graphic that shows the elevation of an installed air column solution. As you can see, the air is injected directly to the plenum, and duct would be assigned depending on what is necessary to cover the square footage of UFAD plenum to be covered. But this design concept allows for the 8-inch, the 10-inch, 12-inch plenum height considerations that to offer a lot of advantages and cost savings to building owners. The manufacturer we deal with, Airfixture, has their own sound testing chamber, so sound tests can be performed for a given design to make sure the owner is confident that the unit laid out will meet the design criteria for the project to reduce noise on site. So closing, we want to cover one of the biggest concerns of UFAD system, and that's plenum leakage. And this is one of the topics that has really challenged projects. I've installed a number of these systems, and unless leakage is addressed properly under the plenum, then it is very difficult to control plenum pressurization under the floor. So you want to look at wherever drywall comes into direct contact with the floor and make sure that that drywall is properly sealed. It's amazing how small orifices can result in leakages cumulatively throughout the floor plenum. You want to look at columns and where drywall comes to the floor. You want to look at making sure that any duct entry points are properly caulked and sealed. Being part of a team to educate contractors on what to pay attention to, I've done before. We did that at the Madison Adaptive Reuse Project and educated the subcontractors that they're part of the mechanical team, that any penetration they make through the plenum has to be properly sealed, and we give them instructions on how to do so. So here are some visuals on how to properly seal penetrations through a floor to make sure there's zero leakage. You can see conduits need to be sealed. If there is a conduit up a wall that penetrates a floor tile, that has to be sealed. Otherwise, cool plenum air will get into the plenum or the wall cavity, and it will bias the thermostat. The thermostat will condition to the wall temperature and not the space temperature, which is not conducive to a successful project. All columns need to be sealed where there might be a penetration, so again, to reduce any issue of leakage. And carpet tile needs to be properly installed to minimize the leakage through the floor that, if not addressed, could result in some imbalance of plenum pressures due to leakage points across the floor. So that's an end of today's presentation. We looked at airflow and pathogen migration, the various influences on HVAC design that are being taken into consideration in the future. We looked at underfloor air systems. We looked at design considerations, the types of air handlers used to serve underfloor air systems. We looked at leakage, and that is it for today's presentation. Are there any questions?
Yes, we have questions. All right. So, are there any operating rooms or a cleaning room with underfloor systems installed anywhere in the world?
Not to my awareness, and I think you would want to be cautious of an operating room because of any spillages or anything that might occur through the floor into the underfloor plenum. That might be a challenge in an OR. The logic certainly makes sense, is to create an environment that is conducive to reducing HAIs, hospital-acquired infections during surgery. Makes all the sense in the world. However, operating rooms use clean room air distribution technologies to create a piston of air across the patient zone on the table that hopefully, if properly laid out, will reduce the risk of infection. But for UFAD applications, I don't know that it would be recommended.
All right. The next question came in, I believe, when you were on the picture that was provided by Tate. What is the floor structural load capacity?
The floor structural load capacity?
Mm-hmm.
I don't have that number to mind. The floor manufacturer that we've had the closest working relationship with is Tate. They can provide that answer very quickly. I do know that these underfloor is the most common design for casinos, and forklifts drive over these floors. Now, to what weight capacity they have to be limited to, I couldn't answer that question.
How is the floor vibration controlled?
I'm not aware of floor vibration. If we're talking about potentially being transmitted from the fan of an air column or an air handler, the fan vibrations these days with our ECM motor technology and properly balanced fan wheels are minimum. I've not known that to be an issue in any of the UFAD systems that I've been involved with at ASU, Maricopa County, churches that I've been involved with. I've not heard that one.
Okay. Doug with Tate just commented, he said concentrated load from 1,000 to 4,000 pound panels. Thank you, Doug.
Thank you very much.
What about heel tripping on the floors? Heel tripping. I'm assuming like a woman's high heel.
Yes, yes. The free area of the diffusers are such that heels cannot be trapped or caught into the faceplate. They're narrow enough where that has not been an issue in any of my experiences with these. And this is in casinos, professional work areas, or whatever. The free area at the diffusers are properly designed to avoid that from being an issue. There is the diffuser itself might rise above the floor carpet 1/16th or 32nd of an inch, but I'm not aware that it's contributed or been conducive to any tripping incidents. I've certainly seen it.
Well, I'm the clumsiest person out there, and I don't think I've ever tripped on one. So, one more. How is the plenum cleaned?
How is the plenum cleaned? Well, that is a good question. I have not heard that being an issue. Because the plenum is sealed through the floor, you don't have ambient dust migrating through the floor panels to the floor. If we have any of the air fixture people on today's presentation, maybe they can answer that more effectively, but I'm not aware that there's any cleaning requirement or recommendation to be done periodically in UFAD systems.
Yeah, I don't think any of them were able to jump on today.
I know for a fact that because you have air supplied through the diffusers, that particle sizes that one would be concerned about for dust cannot be injected back into the space that the low discharge velocities the diffusers provide. So if there's concern that over the years there might be a dust buildup under the floor, and that dust will be injected into the breathing zone of the occupants, there's no evidence to support that. In fact, the evidence suggests just the contrary. That dust stays localized.
I think that question popped up when you were talking about U of A and like students pouring soda down the diffuser. So in that case, I feel bad for the person who has to clean it.
Yeah, but if somebody did feel that way inclined and you didn't have a ducted solution, the floor, the tiles, the 2x2 tiles come up very quickly. You just pull them up and mop it up and put them back down, and then you just lay the carpet pieces back in place.
Okay, as if somebody spilled the soda on the floor itself.
That's correct.
Okay. Yeah, I believe that's when that question popped up. So if I misunderstood any of the questions that come through, always feel free to correct me. If you have any other follow-up questions, Dan is always available. If you don't have his contact information, feel free to email me and I will get you in touch with him. But that is all the questions that we have today.
Well, thank all of you very much. Kelly, thank you. And I wish you a very happy holidays and a safe holidays this coming season.
You too. Yep. And thank you everybody for joining us. And as Stan said, happy holidays and look for our 2024 schedule coming out soon.
Thank you very much.
Thank you, everybody.
Thanks very much.